Now let's consider the ground state of helium atom as a case of variational method being applied in quantum mechanics. As you know, helium atom consists of 2 unit positive charge in its nucleus because of the presence of 2 protons. I am not going to represent any neutron in the nucleus as long as neutron has no relevance as in the regime of our discussion, and there are 2 electrons revolving around this nucleus having, say, minus E charge. And most often we may use it to visualize that these electrons will be occupying the diametrically opposite points because of their mutual repulsion. Now this system could be viewed as these 2 electron species that are revolving around the nucleus. And often we account for the Hamiltonian in terms of the Hamiltonian or the total energy of the 2 electrons. In such a context, the system could be taken as the sum total of 2 hydrogen-like electrons, so that the Hamiltonian of the system can be taken as the sum of the Hamiltonian of 2 hydrogen atoms with a modified charge for the nucleus being, say, represented by Z, the atomic number of helium. Of course, it is nothing other than, say, 2, as I have represented here. So the Hamiltonian of the system may be written as the Hamiltonian of first electron occupying at a position vector of, say, R1 plus Hamiltonian of the second electron occupying a position having a position vector, say, R2. So that the Hamiltonian of the first electron may be written as minus h bar square by 2m del square. Instead of del square, I will be specifying it in terms of, say, del 1 square plus potential energy of the first electron. That is, again we will be considering the problem in CGA system so that we can eliminate the constant part 1 by 4 pi epsilon 0 into charge of the nucleus. I will be representing this as a Z into E positive into charge of the electron minus E. Overall this potential will be then minus Z E square divided by R1. Similarly, we can have a Hamiltonian for the second electron minus h bar square by 2m del 2 square minus Z E square divided by R2. Here there will be one more perturbation part also for the Hamiltonian that arises from the mutual repulsion between the 2 electrons occupying the diametrically opposite points, and the relative position vector of one among these electrons with respect to the other is position vector of the first one minus position vector of the second one, and the separation will be then clearly R1 minus R2. Of course, we will be representing this as a modulus, and we will be abbreviating this using the representation R12, position vector of the first one with respect to the second one, or vice versa, as I have represented a modulus symbol here. And this interaction energy will be equal to charge of the first electron minus E into charge of the second electron again minus E divided by R1 minus R2. Make it overall a repulsive interaction represented by a positive side plus E square divided by R12. So the Hamiltonian of the system is rather simple, or say rather simplified. Now to apply the variational method, we will have to first of all identify the most suitable trial wave function representing these 2 electron species, or rather these 2 hydrogen atom-like species. For that, we will be considering the physical inductions about the problem. It is, as I have told you, 2 hydrogen-like electrons are there. 2 hydrogen-like Hamiltonian could be then taken along with the interaction potential as the Hamiltonian of the system. Now what about the wave function? The wave function can also then be the product of two hydrogen-like wave functions. We have seen the wave function representing hydrogen atom in the earlier problem as phi equal to, once it is normalized, you have a normalization constant 1 by square root pi a cube, 1 by root pi a cube exponential minus r by a in the ground state. Here also in the ground state you can have a similar wave function representing the first electron, and an identical wave function could be taken to represent the second electron as well. Then for the overall system, the wave function could be taken as the product of these two hydrogen-like wave functions representing the two electrons in the system. And here we'll have to incorporate the nuclear charge also taken into consideration, so that for one electron or for any electron among these two, though I have represented it is for first electron, the wave function can have a representation like this square root of z cube by pi a cube e raised to minus z r divided by a. A similar wave function can be there for the second electron. For that you will have to replace this one symbol by means of 2, and instead of r, for the first one you might have used R1 and for the second one you might have used R2. Here also you will have to account for this modification, and A is nothing other than the Bohr radius as we have already seen in the case of hydrogen atom. So that the overall wave function representing the system may be written as phi1 R1 into phi2 of R2. That will be then modified as root z cube by pi a cube e raised to minus z r1 by a into square root z cube by pi a cube e raised to minus z r2 by a. Of course, the square root will be vanishing. We will have z cube by pi a cube, and the exponent terms could be combined as e power minus z by a into r1 minus r2. But did we incorporated any adjustable parameter? That will be forming the most vital part of guessing a trial wave function, and will be evidently the most vital part of the variational method as well. We have not yet incorporated any adjustable parameter. Then what adjustable parameter that we'll have to incorporate as long as the system is concerned? Yeah, it is the screening of nuclear interaction due to the presence of the other electron as long as any particular electron is concerned. See, we already have an electron here, and if we are assuming that there is only one electron in the species, then this electron will not be suffering any repulsion from the other electron. This will cause a single attractive pull from the nucleus by the electron. However, in the presence of the second electron, or I must tell you the latter electron, the effective attraction suffered by the former electron or any one among these two electrons will be diminished or will be reduced by a certain amount. This kind of a diminishing or a decrease in the effective attractive pull suffered by one of the electron in the helium atom due to the presence of the other electron. See, this will be mutual for both of these two electrons. Due to the presence of the other electron, any one among these two electrons will be experiencing a diminished attractive pull that might have been a greater attractive pull in the absence of the other electron. This effective reduction in the attractive pull from the nucleus of the helium atom being suffered by one of the electron due to the presence of the other electron is, as usual, referred to as screening effect. This is something that you have already learned in your chemistry classes. For the F block elements, you can have this as a very prominent effect that will be affecting the chemical properties of the species as well. This is usually referred to as the screening effect of the nuclear pull. Though it is taken in a different context in your discussion on periodic table, we have the screening effect with this kind of a context. So due to the presence of the second electron, the effective attractive pull suffered by the first electron will be diminished. This can be mathematically projected in a different manner. Though the nucleus has a charge, say 2 unit positive charge, the effective attractive pull suffered by any one among these two electrons will be assuming the nucleus to have a charge less than the 2 unit positive charge. This indicates that due to the presence of the second electron, the effective nuclear charge felt by any one among these two electrons will be modified from Z to an effective nuclear charge or effective atomic number. Rather than atomic number, I must tell you nuclear charge, say Z prime. And this parameter is taken as the adjustable parameter as long as the application of variational method to helium atom or to the case of helium atom is concerned. So in all these locations where you come across this nuclear charge, we'll be replacing them by means of Z prime, the effective nuclear charge. That modify the wave function, say phi, representing the ground state of helium atom as Z prime cube by pi a cube e power minus Z prime by a into R1 plus R2. If we have modified or transformed the wave function from one containing Z to another one containing Z prime, we require to have a similar modification for the Hamiltonian also. The Hamiltonian is given by minus h bar square by 2m del 1 square minus Z e square by R1 plus minus h bar square by 2m del 2 square minus Z e square by R2 plus e square by R12. I'll have to incorporate Z prime to this expression. For that, what I am going to do is that I'll be adding and subtracting all these terms in the expression for Hamiltonian containing Z being modified in terms of say Z prime. So that for corresponding to this term Z e square by R1, I'll be adding Z prime e square by R1 and subtracting Z prime e square by R1. And this is shown in the next slide. So what we have to do is that h equal to minus h bar square by 2m del 1 square minus Z prime e square by R1 plus Z prime e square by R1. These are the terms that I have added and subtracted. Already there is minus Z e square by R1. Similarly, we do it for the second electron or hydrogen like electron, minus h bar square by 2m del 2 square minus Z e square by R2 plus Z, this term is already there, plus Z prime e square by R2 minus Z prime e square by R2. What I have added is I have subtracted 2 plus e square by R12. Now we will modify the Hamiltonian in terms of say Z prime as minus h bar square by 2m del 1 square minus Z prime e square by R1 plus minus h bar square by 2m del 2 square plus minus Z prime e square by R2. And upon writing this, I have taken this term and this term. Then I will have to account for these two terms. See, e square by R1 is common for both of these two terms. E square by R1 is taken out, then e square by R1 into what remains is Z prime minus Z. Similarly, in this, I have taken this one along with this one. So I'll have to combine these two terms, e square by R2 into Z prime minus Z. Once again, this is positive term and this is negative term. So e square by R2 into Z prime minus Z plus the interaction energy e square divided by R12. So the first step of applying variational method is almost done. Now we will evaluate the energy in terms of the variation. So now we will evaluate the ground state energy of helium in terms of the adjustable parameter, as the expectation value of the Hamiltonian that is being modified using this expression with respect to the wave function that we have already formulated, or trial wave function that we have already formulated. And keep in mind here that this is already a normalized wave function, because we have separately normalized the two hydrogen-like wave functions, say phi1 and phi2, so that there is no question of the denominator part as long as the Rayleigh-Ritz formula is concerned. So this is now equal to scalar product phi h phi, that is equal to scalar product phi1 phi2. H is written here, say minus h bar square by 2m del 1 square plus etc. All these say 4 plus 2, 6 plus 7 different terms are to be separated. So this is for first electron and this is for second electron. This is for the interactive addition that we have accounted both these two terms, say being marked as a T3 and T4, and this is the interaction potential or the energy evaluation corresponding to interaction potential. So this is scalar product phi1 phi2 Hamiltonian of the first electron plus scalar product phi1 phi2 Hamiltonian corresponding to this term being marked as a T2, and corresponding to this one being marked as a T3, and corresponding to this term being marked as a T4, and finally corresponding to this one being marked as a T5. Now look at this term, first one. This operator consists of two, or operator domain consists of two different operators, del 1 square and r1. Both these are functions of r1 only, and in the wave function domain or vector domain there are both phi1 and phi2. However, this operator del 1 square or r1 has nothing to do with this wave function phi2. Similarly, for this term, this operator is del 2 square and r2. These are explicitly depending upon r2. So that these operators has nothing to do with the wave function, say phi1 or phi1 in the ket space or adjoint ket space. So they can be taken out. Similarly, for this term, the operator has dependence only over R1, so phi2 can be taken constant. Similarly, for this one, the operator has dependence only over R2. R2, the operator has nothing to do with the wave function phi1, which is an explicit function of R1. So phi1 from the ket space and adjoint ket space could be taken out separately. However, in this case, R12 is an operator that depends on both R1 and R2, as R12 is equal to modulus R1 minus R2. So for this term only, we will have to account for an operation over phi1 and phi2 separately. And another important thing is that, see, the evaluation of T1 we have already done in the case of the earlier problem that we have just solved in the last class. That is the evaluation of the ground state energy of hydrogen atom. The operators are exactly identical, with the only modification being there is a Z prime term in the potential energy term, and we will have to account for that modification only. That we will be doing very shortly, and there is modification for the wave function also. And again, the term 1 and term 2 are exactly identical. We have just transformed the operator that is depending over R1 to R2. That will be never affecting our calculation. So it is a bonus that once you have calculated the energy corresponding to term 1, the same amount of energy can be written for term 2 also. This is true in the case of term 3 and term 4. Because for term 3 the dependence is over R1, and in term 4 this dependence is modified to R2 only. So here also we will be evaluating only one among these two. The energy for the other one will be exactly equal, and this term is to be separately evaluated. This I have represented here as a T1 equals T2, T3 equals T4 in terms of the energetics, and now we will evaluate this separately, T1 and T2. For the time being, let me evaluate this term, say T1. I have told you the operator has dependence over R1 only. So phi2 can be taken out from the K space and adjoint K space as a scalar product phi2, phi2. This is nothing other than the normalization condition for phi2. So scalar product phi2, phi2 is nothing other than 1. What remains is scalar product phi1 minus h bar square by 2m del 1 square minus z prime e square divided by r1 get phi1. This is to be evaluated. For that we will be substituting phi1 as a square root z prime cube by pi a cube e power minus z prime r1 divided by a. That is square root z prime cube by pi a cube e raised to minus z prime r by a. All these terms consist of z prime other than those operator part where we have accounted an addition and subtraction. If I have forgotten to put a prime symbol, please keep in mind that there is a prime symbol for all these z terms. Minus h bar square by 2m del 1 square minus z prime e square by r1. In the K space, we have square root z prime cube by pi a cube e power minus z prime r1 divided by a. So, root z prime cube by pi a cube is constant taken from both K space and adjoint K space is purely real. There is no question of any complex conjugation then coming out of the constant part from the adjoint K space. Then this becomes z prime cube by pi a cube. Yeah, I have a lot of brackets here. Integral 0 to infinity, 0 to pi, integral 0 to 2 pi corresponding to say theta part and phi part respectively. These two integrands are there. E power minus z prime r1 by a minus h bar square by 2m del 1 square e power minus z prime r1 by a r1 square d r1 sin theta 1 d theta 1 d phi 1 minus potential energy part integral from 0 to infinity. This is a common factor for both these two terms. That is why I have another curly here. Integral 0 to infinity, integral 0 to pi, 0 to 2 pi, e power minus z prime r1 by a. Potential energy term z prime e square by r1. I have already accounted this minus here. E power minus z prime r1 by a r1 square dr1 sin theta 1 d theta 1 d phi 1. Integral d phi 1 will give me 2 pi. Integral sin theta d theta will give me 2. Overall 2 into 2 pi, 4 pi is common for both these two terms that are taken out. 4 pi z prime cube by pi a cube. Integral 0 to infinity. Yeah, minus h bar square by 2m I have put aside here. Minus h bar square by 2m. Yeah, here we will be using this result that I have told you while we talked about the hydrogen atom. Minus h bar square by 2m del square psi is to be evaluated. Del square psi integral from 0 to infinity. This we have proved as a result as identical to h bar square by 2m integral 0 to infinity grad psi star dot grad psi. We will be making use of this result here. So grad psi star is grad is to be accounted in terms of say grad 1 or del 1. Del 1 of psi star. Psi star is the same as psi because psi is purely real parameter. H bar square by 2m is written here. This I will be taking out very shortly. and grad psi, that is grad of e power minus z prime r1 by a r1 square dr, minus potential energy term becomes z prime by r1, z prime e square is constant. We will be taking it only in the next step out. Integral 0 to infinity e power minus z prime r1 by a z prime e square by r1 e power minus z prime r1 by a r1 square dr. So 4 pi can be vanished here. Anyway, we keep them for another step. 4 pi z prime cube by pi a cube. Integral 0 to infinity gradient of this one, that is exponent into minus z prime divided by a. And here also the gradient generate me a constant term minus z prime divided by a. Overall that will make it up say minus z prime by a whole square. H bar square by 2m is also kept here. Now these are constants. Minus z prime e square is taken out from this term. Integral 0 to infinity e power minus 2 z prime r1 by a into e raised to minus z prime r1 by a. The operator is 1 by r1, that will be vanishing with this one, and it is a commuting operator with exponent as well. So these are directly multiplied. E power minus 2 z prime by z prime r1 by a into 1 r1 will be vanishing with the square term here to make it say r1 dr. So 4 pi z prime cube by pi a cube, this is integrated. Before that, we have these constant terms taken out. Z prime square by a square is bar square by 2m. This integral is n factorial divided by n factorial corresponding to say r1 square term where n is 2. So 2 factorial, that is 2 divided by a power n plus 1. A is the coefficient of minus r1 in the power of exponent term. That is 2z prime by a. So 2z prime by a whole power 3. So this integration is over. Now this term z prime e square into n factorial, n is 1 here, 1 divided by a power n plus 1. A instead of a I have 2z prime by a. 2z prime by a whole power n plus 1. N is 1. So 1 plus 1, that is 2. Now this pi is vanished. I'll be taking 4 to the bracket. So what remains is, here there is a clarity change. It is z prime cube. Apologies for the limited resources we do have. We will have to make use of these apps every here and then. A prime cube, z prime cube by a cube is there. Now pi has gone, 4 is taken to the bracket. Here I'll have 4 into 2, 8, then 8 will be vanishing with this 2 cube. So 2 cube, 2 and 4 have gone. What remains is h bar square z prime square by 2m a square. Yeah, z prime also will be vanishing. I have a z prime cube here, so z prime comes to the numerator. So h bar square a comes to the numerator, a square will be vanishing with a cube and 1 a remains, that comes to the numerator. H bar square a divided by 2m z prime, 2m z prime, minus this term becomes z prime goes, a comes to numerator, a square come to numerator, a square e square divided by 2 square into 4 is there, so this 2 square also will be going. What remains is e square a square divided by z prime. So this is the ground state energy obtained in terms of the adjustable parameter z prime. As long as the first term or first 2 terms are concerned, these 2 energies are exactly identical. We modify them. H bar square z prime square by 2m a square minus z prime square e square by a. So z prime square could be taken as a common factor, and we substitute for a, the Bohr radius, as h bar by m e square. Z prime square is taken out, h bar square divided by 2m into a square is there, a is h bar square by m e square. So a square is square of this one. Minus z prime square e square divided by a is h bar square divided by m e square. Already I have taken z prime square out. So this term is not there. Now Z prime square into, this could be modified. M vanishes. E square e power 4 come to numerator. H bar square in the numerator vanishes. So this becomes M e power 4 divided by 2 h cross square. Minus here also e square, m e square come to numerator. M e power 4 divided by h bar square. So m e power 4 by 2 h bar square minus m e power 4. So we take z prime square out. What remains is m e power 4 by 2 h cross square minus m e power 4 by h cross square. Make it say minus m e power 4 by 2 h cross square. And this is nothing other than the ground state energy of hydrogen, as we have seen in the earlier problem. So let me write now WH equal to m e power 4 by 2 h cross square, the magnitude of the ground state energy of hydrogen in electron volt, which is, as you know, 13.6 electron volt. So that we will rewrite this as a minus, see, the magnitude is written as a WH minus Z prime square WH. Now, the first two terms are evaluated. Let's see the evaluation of term number 3 and term number 4. That are also exactly identical. The terms are either in terms of R1 or in terms of R2. Once again, let me evaluate the term in terms of R1. And since the operator is in terms of R1, it has nothing to do with the R2 dependent homogeneous part of the wave function. So phi2 is taken out of the adjoint get space and get space. Make it say normalization of phi2, that's equal to 1. What remains is scalar product phi1 z prime minus z e square by R1 phi1. If you are evaluating T4, you will have say phi2 here, phi1 will be taken out upon normalization, and instead of R1 you will have R2 here, and in this evaluation you will have phi2 instead of phi1. Now we substitute for phi1 square root z prime cube by pi a cube e power minus z prime R1 by a. Z prime minus z e square by R1. Here z is without prime, that is the actual atomic number or nuclear charge of the helium nucleus. E square by R1 square root z prime cube by pi a cube e power minus z prime R1 by a. So these constants are taken out of the get space and adjoint get space. Make it say square root vanishes, z prime cube by pi a cube, z prime minus z e square is also constant, it is taken out. What remains is integral 0 to infinity this exponent term into 1 by r1 into this exponent term e power minus z prime r1 by a, and into the volume element r square, that is r1 square dr1 integral sin theta d theta d phi. These integrants are evaluated as we have done it so many times, which make it say 4 pi, and r1 square vanishes with r1 in this denominator. This also we have repeated several times. So 4 pi is written here, pi vanishes for z prime cube, z prime minus z e square by a cube. A cube is also written here, pi vanishes. Now this integral e power minus 2 z prime r1 by a r1 dr. Make it say 1 factorial over 2 z prime by a whole power 1 plus 1. Make it say 2. Upon simplification, z prime cube and z prime square is there in the denominator. Z prime remains. 2 square vanish with 4. A cube and a square vanishes, a remain in the denominator. So this term becomes z prime minus z e square by a. Z prime into z prime minus z e square divided by a. So term number 3 and term number 4 are evaluated. Now we will substitute a equal to h prime square by m e square here. That make the expression simplified as a z prime into z prime minus z e square. E square and e square coming from the denominator, make it say e power 4 into m is there. So m e power 4 by h cross square. There is a deficit of 2 for writing this to be modified as the magnitude of the ground state energy of hydrogen. So I have supplied these 2 in the numerator and denominator. So this quantity in this bracket is now the magnitude of the ground state energy of hydrogen WH. So this may be written as 2z prime into z prime minus z wh. Keep in mind term number 4 is also exactly this one. So overall in the last substitution this will be doubled. Now term number 5. This is the term containing both the operator R1 and R2. So you cannot account for any normalization because this operator has to operate over both these vectors phi1 and phi2 in the K space. So scalar product phi1 phi2 E square by R1 minus R2 phi1 phi2. This upon the integral language modified as phi1 and phi2 are taken out. In phi1 there is root z prime cube by pi a cube. In phi2 also there is this term. So overall there will be square root of z prime cube by pi a cube whole power 4. Make it say z prime cube by pi a cube whole square. Square root vanish with squaring. One squaring operation. E square is taken out. Integral 0 to infinity 0 to pi 0 to 2 pi e power minus 2 z prime by a into r1 plus r2. All these terms are incorporated here, divided by r1 minus r2, r1 square, r2 square, dr1, dr2, sin theta, d theta 1, sin theta 2, d theta 2, d phi 1, d phi 2. This make say 2 pi into 2 pi, this make 2 into 2, 4. So 4 into 4 pi, make it, yeah, it is written here. 2 into 2 into 2 pi into 2 pi into this one into, in the integral, this will be remaining. For this, we will be decomposing 1 by r1 minus r2 or 1 by r12 in terms of the Legendre polynomial. This I think you have discussed once you talked about the hydrogen atom problem in quantum dynamics or three-dimensional cases, as you talked about the three-dimensional problems in quantum mechanics in semester 2 quantum mechanics 1 paper. So overall these terms becomes 16 z prime cube whole square z prime raised to 6 e square divided by a power 6. Pi square is here. Pi square will be vanishing with these two pi's. Integral 0 to infinity e raised to minus 2 z prime by a into r1 plus r2 by r12 into this volume element terms. Now we split 1 by r12 using these Legendre polynomials. Say 1 by r12 equal to in summation L from 0 to infinity m from minus 1 to 1 4 pi by 2L plus 1, where L is the orbital angular momentum quantum number of helium or hydrogen-like species. YLM star, YLM complex conjugate theta comma phi, YLM theta comma phi, where YLM theta phi is the spherical harmonic solution. Substituting this and simplifying this using the orthogonality property of Legendre polynomials, you can evaluate this energy to be equal to say pi by 4 z prime wh. This is positive energy plus pi by 4 z prime wh. This is a repetition of what you have done in three-dimensional problems. For the time being, you can evaluate this and submit it as an assignment. Assignment problem. Substitute 1 by r12 equal to this one and evaluate this integral as a pi by 4 z prime wh. If you are interested, you can refer to Applications of Quantum Mechanics by G. Aruldas. So we have now evaluated all these terms. Now let's substitute these terms in the expression for the ground state energy of helium in terms of the adjustable parameter. First two terms are found to be minus z prime square wh. So T1 plus T2 make it say minus 2 z prime square wh. Second, third term and fourth term are found to be say 2 z prime into z prime minus z wh. So their summation will make it say 4 z prime into z prime minus z into wh. And the fifth term is pi by 4 z prime wh. So wh is common and is taken out into 2 z prime square minus 2 z prime square plus 4 z prime square make it say 2 z prime square minus 4z prime into z minus 4z z prime plus pi by 4 z prime. If you are interested, you can take z prime also out. That will help you in the further simplification. Yeah, I have taken it here out. WH into 1z prime is taken out. 2z prime minus 4z plus pi by 4. Now apply the minimization. Derivative of this one with respect to z prime is 0. For the sake of simplicity, I have taken the derivative of this term, and this I have put aside for a simplification that is yet to come. So 2z prime WH is a constant, so there is no question of any function of function. I'll have to account for the derivative of this one only, and I have equated this to 0 so that WH could be omitted. So 2z prime square has a derivative 2 into 2 4z prime minus 4z constant into z prime has a derivative 1 plus pi by 4 z prime make it say pi by 4. This is equal to 0 means z prime, the adjustable parameter, equal to, take the remaining terms to the right side. So 4z prime equal to 4z minus 5 divided by 4. So that z prime equal to, divide this by 4, make it say z minus 5 by 4 into 4, 16. So this is the effective charge of the nucleus being felt by both of the electrons in the helium atom due to the presence of the other one. If Z, in helium Z is 2, so effectively this will be less than 2. The nuclear charge being felt by both of the electrons will be effectively less than 2. It will be 2 minus 5 by 16 approximately. Now we substitute Z prime in this expression. Yeah, in this expression. So WH into 2Z prime 2 into Z minus 5 by 16 minus 4Z plus 5 by 4 into Z prime, that is Z minus 5 by 16. See, from this one we can take 4 out. Then this becomes I have not shown that step. I have taken Z minus 5 by 16 common from this term and from this term. Yeah, I can do it here also. Z minus 5 by 16 is taken out. What remains in this term is 2. Minus in this term, Z minus 5 by 16 could be taken upon a simplification. Suppose I am taking minus 4 out of this one. So minus 4 into these two terms, minus 4 into Z minus 5 by 16. Exactly, it is minus 4 into Z minus 5 by 16. And after writing this, I have taken Z minus 5 by 16 out. So in this term 2 remains, and in this term minus 4 remains. 2 minus 4 is written here into, this is repeated here, Z minus 5 by 16. That is 2 minus 4 make it minus 2 into Z minus 5 by 16 whole square WH. This is assumed to be the ground state energy of helium being evaluated within the certainty limits of the variational method. We substitute Z equal to 2 and WH equal to 13.6 electron volt. You will obtain a determination of the ground state energy of helium as a minus 77.46 electron volt. You just put this is equal to 2 and this is equal to 13.6 and calculate this value. This comes to minus 76.46 electron volt. And the experimental value of the ground state energy of helium is found to be minus 78.975 electron volt. This value is in agreement with this one. And this once again tell you, of course the accuracy is limited here, there is an error in the determination. However, we have already seen that this calculation made by variational method always give you an upper limit of the ground state energy. It is exactly true here. What is wrong with the method is that our wave function or assumption of the wave function has less matching with the actual wave function representing the helium atom. However, within the limits of the accuracy of variational method, this give you a better calculation. And Hilaris has taken a different wave function of the form square root of z cube divided by pi a cube pi a cube into e power minus z by a into r1 plus r2, and using this wave function he was able to evaluate the ground state energy of hydrogen as equal to helium as equal to minus 78 electron volt. So this is not a failure for the method. This in fact represents all the beauties of the variational method. If you are taking a better approximation, this will give you a better solution, and if you have taken a less matching approximation for the wave function, it show you a lesser